Okay, now I have given you sufficient introduction to various types of methods available to us. Force method, displacement method. Force method, if it is applied to linear elastic structures, we call it as flexibility method. Displacement method, when applied to linear elastic structures only, then we call it as stiffness method of analysis. Now we will see the stiffness method for the beams, trusses, frames. Only simple topics they will ask you in the exam. We don't have to use the Castigliano's theorem 1 to find the displacement coefficients or force coefficients, because to that extent you will not have time, but you must have the idea from where those came. But in the exam you have only 30 seconds or 40 seconds time. So whatever strength of materials formulas you have learned, only those formulas you are asked to give. Those numbers you have to give specifically, that's all. So first we'll take up stiffness matrix method. Stiffness K. In our strength of materials, you have studied the stiffness of a spring and also stiffness of a beam, means load required to produce unit displacement. Then in moment distribution method, you have studied moment required to produce unit rotation. You call it as stiffness factor or simply stiffness. So depend for each type of loading, corresponding stiffness we can find. So stiffness K means load required. This load can be a force or it can be a moment. Load required to produce unit displacement. That displacement again can be linear displacement delta or angular displacement theta. So accordingly, we name the different stiffnesses. Okay. So load required to produce unit displacement is called stiffness. Now we have studied in strength of materials axial stiffness of a spring. You call it as K. Load required to produce unit displacement means W by delta. Strength of materials, you have studied the helical spring deflection. What is that deflection? 64 W R cube N by C d to the power of 4 or N d to the power of 4 or G into d to the power of 4. C and G, anything we can use there. R means mean radius of the coil. N means number of turns in the coil. D means diameter of the spring wire. C means shear modulus. W is the load applied. This is the deflection of the spring. So then you get from this one C d to the power of 4 by 64 R cube N. This is the axial stiffness of a spring. In the torsion chapter again you have studied torsional stiffness. Torsional stiffness of a shaft. K. Torque required to produce unit twist T by theta. Torque is, what are the units? Torque, if you take it as Newton meter per radian, per unit radian. Torque required per unit radian. These are the units. Here simply Newton per mm. Okay. Now this is the torsional stiffness. Then you have studied flexural stiffness of a beam. Flexural stiffness of a cantilever beam. Cantilever beam loaded at free end. K is equal to W by delta. Now you see this is the load W, length is L, it deflects, this is the delta. This is WL cube by 3EI. So W by delta means W by WL cube by 3EI. So you will get 3EI by L cube. This is the flexural stiffness of a beam subjected to point load at free end. Same that flexural stiffness, if you want to find flexural stiffness of a beam when it is subjected to moment, then the moment distribution method I have given m by theta, moment required to produce this one, EI by L, you got it. This is the flexural stiffness of a cantilever beam when subjected to moment. Cantilever when subjected to moment. So stiffnesses are different types. Corresponding to each loading, you can get a stiffness for that. That means load required to produce unit displacement. That displacement can be linear displacement or angular displacement. Correspondingly, it can be W or it can be M. So this is what you have studied in strength of materials, moment distribution method, and torsion chapter, etc. Now in the matrix method, instead of writing like this torsional stiffness, flexural stiffness, you will give the numbers to all the possible displacements. Then where you apply load and where you are finding the displacement. Accordingly, the stiffnesses are defined. Okay. So your second point is types of stiffness. I remove this one. Second concept, types of stiffness. To find this one, what we do is we take, supposing that we have a cantilever beam. This is a B. This you take coordinate 1. That means possible displacements, you give numbers to them. Coordinate 1 means in this direction what displacement can happen? Elongation. This I will give coordinate 2. What displacement can happen in the 2 direction? Deflection. And it can also rotate, coordinate 3 for rotation. It can also get twisted. So twisted means I can show it like this. So like this, for all possible displacements, you have to give the numbers to them. Then whatever you have studied in SM, you will write them in a systematic manner. Coordinate numbers are given to all possible displacements. All possible displacements only. In this case, what I have given is coordinate 1 I have given for elongation. Don't want, you can give coordinate 2, instead of 2 I can write 1, 2, 4, 3. Any number you can give it, arbitrarily chosen numbers they are, not necessarily 1 is always for elongation. 1 can be deflection, 2 for elongation, like that. So 1 for elongation I have given here like this, 2 for deflection, 3 for slope, 4 for angle of twist. So these are all the possible displacements I have given. Coordinate, 4 coordinates only we have taken, let us say. Now you see, we want to find first type of stiffness is axial stiffness. axial stiffness, I call it as K11. This is force required. K1 means force required at coordinate 1 to produce unit displacement at coordinate 1. That's how we have to read. Force required at coordinate 1 or force developed at 1 because of the displacement. Any which way we can read it. If I give unit displacement, how much resistance or force is developed in the member in the direction of the displacement? That resistance, how much it offers, or how much force is developed because of your displacement. So we know from strength of materials this one. We don't have to use our Castigliano's theorem. 1. Force required at coordinate 1 to produce unit displacement at coordinate 1. Unit displacement at coordinate 1. When you will find after fixing all the displacements. After fixing all other coordinates. After fixing all other coordinates. What it means is, it's like this. Supposing that you have this point is A, this point is B, length is some L. Now, see, after fixing all other coordinates means it is a symbolic representation of fixing all other coordinates. It is not a fixed support, as in the moment distribution method I told you. First we will fix the coordinates, fix the joints. Actually they are not fixed. We assume that we fix them. Unnecessarily we fix them, then we release them. Same process everywhere in the stiffness methods. It is simply a symbolic, this is a fixed support, but here blue color one is a symbolic representation of fixing all other coordinates. Don't permit joint B to deflect. Don't permit it to rotate. Don't permit it to get twisted. Without permitting all other displacements, hold it, pull it by unit displacement. Then how much force is developed or how much force is required for that process? That we call it as stiffness. Stiffnesses are always defined that way. All other displacements you prevent them. Whatever stiffness you wanted, for that only give unit displacement and find how much force is required. And that force required is not beyond your strength of materials concepts. This is, well, now I think I have given you this point. This is your coordinate 1. This is coordinate 2, coordinate 3 and coordinate 4, right? So this is not a fixed support, you have to take it. It is a symbolic representation of fixing representation of fixing all other coordinates. Then apply unit displacement. Now you see, don't permit it to deflect, don't rotate, don't twist, hold, pull by 1. Then how much force is required for that is the axial stiffness. Now if it comes here, let us say, it can come because it's not a fixed support, so symbolic representation only. This is delta 1, this value is 1. Then what is the force required? Force at coordinate 1, K1 means force at the coordinate 1 developed. Because of what? Because of the unit displacement. Force developed at coordinate 1 to produce unit displacement also at 1, K11. This is K11. That you can find it from strength of materials. You don't have to use Castigliano's theorem too. Now you see K11 if you want it, what will happen? K11 is nothing but for delta 1 is equal to 1. For delta 1 force is how much? For delta 1 is nothing but P1 into L by AE. K11 means force required per unit displacement, P1 by delta 1. Delta 1 means P1 into L by AE. This is what in strength of materials you have studied. AE stands for axial rigidity. Axial rigidity per unit length is called axial stiffness. That same axial stiffness, now you are giving number. That's all. Where you are applying the load, where you are finding the displacement. So accordingly you will get it like this. Okay. Then energy methods are what? K11. If I want to find displacement, let us say some x1 displacement, delta 1 is equal to this dou u by some dou x1. X1 here is P1 force. U means strain energy. If you differentiate partially the strain energy stored with respect to x1, you will get the displacement delta 1. But this is delta 1 is due to x1 force, that means P1 force. I wanted unit force, say, that means I wanted this displacement to be unit. That this is a P1 force. P1 force means strain energy stored with respect to dou u. This is the Castigliano's theorem 1. First derivative of energy with respect to displacement delta 1, you will get force at that point. Right? Now, I want delta 1 displacement to be 1. That means P1 force is because of delta 1 displacement. If delta 1 becomes 1, how much force I have to apply? That means this P1 I differentiate it again with respect to delta 1. So that is called K11, we call it. Dou P1 by dou delta 1. This we will get it as dou square U by dou delta 1 square. Now, if you differentiate P1 with respect to delta, you will get unit force. This is called due to unit displacement, how much force is required. So, dou square U by delta 1 square. This is K11. Now, in the strain energy chapter, I gave you U in terms of strain energy. What is that? Delta square AE by 2L. Now, if I want to find the displacement, dou U by dou delta, P1 is equal to dou U by dou delta. How much I will get? Delta square means 2 delta. So, AE by L into delta. If this is P1 force is required to produce delta displacement. I want that unit displacement, let us say. Then differentiate it with delta again. Dou P1 by dou delta. This you will get because of the unit force K11. If you differentiate with respect to delta, what you get? AE by L. Or this is nothing but dou square U by dou delta square. Now you see, only one axial force case I am explaining how the Castigliano's theorem 1 is used to find the stiffness coefficients. Theorem 1 tells you that if I want to get force dou U by dou delta, I will get some AE by L into delta. This tells you that for delta displacement you have to apply P1 force, that means AE by L into delta. Now I don't want delta, that delta I want it to be 1. Then differentiate P1 with respect to delta. Then I will get force required to produce unit displacement, that is called stiffness coefficient, axial stiffness. So if I differentiate this again with respect to delta, delta differentiation is 1. So AE by L I will get. This is nothing but dou P1 by dou delta means P1 is dou U by dou delta. If I substitute dou square U by delta square. So second differentiation of strain energy with respect to delta gives you stiffness coefficient. First differentiation gives you force for delta displacement. For unit displacement, if you want, again differentiate it with respect to delta, you will get AE by L. This is called axial stiffness, strength of materials, we know. So first chapter, strength of materials, you have studied what is axial stiffness. Then sir might have told you about the strain energy. In the strain energy, gradually applied load, suddenly applied load, impact loading, you have studied. There, that strain energy, if you differentiate strain energy, if you write in terms of displacement, two times if you differentiate it with respect to delta, what you get is called stiffness coefficient. Only one time you differentiate it, what you get is the load required to produce delta displacement. In the exam, because you have only say 30 seconds time for the questions that they ask, you don't have to find strain energy, differentiate to get the unit, to get the axial stiffness. We have studied strength of materials. What we have studied strength of materials? Delta 1 is P1L by AE. Any question in the examination given, they don't go beyond your strength of materials concepts. You don't have to use strain energy concept and find the axial stiffness or flexural stiffness and waste the time. Here I am giving you the way you can get it from SM or from strain energy concepts. That strain energy concepts you will use for big structures where you don't know the formulas. For simple beam, you know already those formulas from the strength of materials. So directly substitute. Why again derive? Waste the time. So delta 1 is P1L by AU, we know. Then K11 means P1 by delta 1, force required to produce unit displacement AU by L. Directly we get it. So in 2 minutes time, your task is only this much. Don't have to find the strain energy in terms of displacement, differentiate twice and waste the time, not required. But you must have an idea of from the strain energy, from the Castigliano's theorem 1, how to get the stiffness coefficients. This is from Castigliano's theorem 1. Okay. This is what you will get. Okay. So axial stiffness cleared. Now we will take the second one, transverse stiffness. Now no strain energy concept, directly we will write from strength of materials concepts. Transverse stiffness. We call it as K22. How we read is force developed at 2 due to unit displacement at 2. How much? So you have to draw the diagram. Again here also symbolic representation of fixing the coordinates, because stiffnesses are defined like that. This is your coordinate 1, coordinate 4 means twist. This is coordinate 2, coordinate 3. So all 4 coordinates, this is simply a symbolic representation. A symbolic representation of fixing all coordinates. So fix all coordinates. Now don't permit it to elongate. Don't rotate. Don't twist. Hold, lift by 1. How much force is required for that is called transverse stiffness. From moment distribution in the fixed beams chapter, I told you about the sinking of supports. That concept will bring it here. Don't have to derive. Now, if I give unit displacement at 2 without rotating, the deflection profile will go like this. It is fixed here. This profile we know how to manage. This is delta 2, its value is 1. I told you whenever you have this type of deflection profile in MDM, sinking of supports, force required is 12 VI delta by L cube. So, to produce this displacement, you require a force of, see, force developed at coordinate 2 or force required at coordinate 2 direction. Then where is the displacement? At 2 only. So force at 2 because of the displacement also at 2. Second subscript where you are giving the displacement. First subscript where you are finding the force. K22 from moment distribution concept 12 VI delta by L cube. This is what I gave, 12 VI delta by L cube. Now delta is 1, so that I can take it as 12 VI by L cube because delta is equal to 1 now. And we also know how much is the fixed end moment developed. How much is developed? 6 EI delta by L square is nothing but 6 EI by L square because delta is 1. Here also how much is developed? 6 EI by L square. Now you see, this curve is developed at which coordinate? Third coordinate. This value, force developed at coordinate 3, 6 EI delta by L square, because of whom? Unit displacement at 2. So we call it as K32. Force developed at 3 due to unit displacement at 2. Force developed at 2 due to unit displacement at 2. That means this reaction, these are all the reactions will develop like that. So this we take it as K32. So K22, 12 EI by L cube. That means this profile, that's why I told you in MDM, whenever you see this type of red color deflection profiles, this formula you must remember. 12 EI by L cube. You cannot derive again by using Macaulay's method of double integration and waste the time. Neither you can use strain energy stored in the beam. Finding the strain energy itself will take again 3-4 minutes time. Then double differentiation, you will get the displacement, you will get the force. That much time you cannot afford. You must do the way I have told you. You have to remember the 12 EI delta by L cube because so many problems we have done in MDM. So by this time automatically you might have remembered that value. That 6 EI delta by L square also you cannot derive. You must know beforehand itself that Macaulay's method of integration. Then Macaulay's method of integration, how it comes, the proof of that means that another 1 hour. So they expect you that these certain fundamentals you know them. Basics only. Not too much complicated things they ask you. If you have to derive, remember that they don't ask you such questions. You must have already known simple things only because your available time, actual calculation available time is only 30 seconds. We have to read the question, you have to understand, then calculate, then tick it. All the things take time. 1 minute you have to finish off. So, such simple questions. So, K22 is 12A delta by LQ. How to read K32 is like this. Force means general term. It can be linear force, angular force. Force developed at first ordinate is at 3 due to unit displacement due to unit displacement at 2. That's how you have to read. Remember that K32 how it has come. Finally, the end result will check how it see that. Okay. Now we have to read wherever you are giving the coordinates, their forces you can find from strength of materials. You give numbers to them. This 6A delta by L square you have to give number like this. 2 means for 12A delta by L cube, whatever you have studied. Now you are giving a number where you are finding the force and where you applied the displacement. Like that you are explaining. This is about transverse stiffness. Third stiffness is flexural stiffness. This K32 it doesn't have any name, simply it is a stiffness coefficient. Now third one is slope. Flexural stiffness. Let us read it as K33. Force developed at 3 due to unit displacement at 3, or you can say force required at 3 if you want to give unit displacement at 3. This also we know from stiffness factor concept I have told you. Again this is A. That's why your MDM, whatever moment distribution method I have given, around 8 hours or 10 hours time, that's why I have concentrated so much on that. This is coordinate 1, 4, coordinate 2, coordinate 3. Again, till you become familiar, you write this one, after that not required. A symbolic representation of fixing all coordinates. Remember again that it is not a fixed support, simply you are holding it like this. Don't permit it to deflect, don't elongate, don't twist, just hold and rotate. How much force is required is called flexural stiffness. Now hold it, rotate it by 1. Then the deflected shape of the beam, because you didn't deflect it, like this it will go. This is a deflection profile. For this deflection profile also I asked you to remember, I wanted this theta is equal to 1. That means delta 3 is equal to 1. This will take it as a displacement at third coordinate, that is nothing but theta. I want that to be 1. For theta to become 1, we know how much is the required. How much moment you have to apply? Force at coordinate 3 because of the displacement at also coordinate 3. For this profile to happen, I told you it is 4EI by L. So K33 is 4EI by L. We change the color. K33 is 4EI by L when far end is fixed. 4EI by L into theta is the moment. If theta becomes 1, 4EI by L. If this is 4EI by L, how much is carried over? This you have to apply. We know how much is developed here. Then it has no number also, because fixed support, there are no coordinates. When there are no coordinates, we don't have to give any number to them. We are not interested at all. But we know that how much moment is developed here, 2EI by L. What is this called? Carryover moment. So 2 here, 4 here, total 6. To balance it, reactions will develop like this. Here how much? 2EI by L plus 4EI by L by L. You will get 6EI by L square down here. Here also 6EI by L square. This I can give a number. Force at coordinate 2 because of what? Displacement at 3, K23. How much force developed? 6EI by L square. This 6EI by L square is not because of the displacement, unit displacement at 2. Then it becomes 12EI by L cube. That is over. Now if I rotate it, this is a 2 marks question. They asked once. A cantilever beam is effective at the free end. It is effectively restrained not to deflect. Then the reaction developed at the free end to produce unit rotation is. So based on the description, first you have to draw the deflected shape of the beam, and the deflected shape of the beam will tell you how much moment you have to apply here and how much reaction will develop here. This is the process of building a 2 marks question. Or they can ask you, as a propped cantilever is subjected to a moment m. To produce unit rotation there, what is the moment required? Simply 4EI by L. That is the description. That's how the questions are asked. That's all. 4EI by L, one year they asked. Another paper they asked, what is the force required in the vertical direction to produce slope, unit slope here? It is 6EI by L square. If you apply this much, theta becomes 1. It should not deflect. That they will give you that without deflection, how much moment, how much force is required to produce unit rotation so that it doesn't deflect. That's it. So you have to draw first diagram, this deflection profile. That will tell you how much moment here, how much force here, how much is the carryover moment. If they ask you because of that, what is the moment developed at the fixed support, say, then you should be able to write 2A by L. Or if they ask you what is the reaction at A, VA. These are all the simple questions they can ask you in the exam. So you must have that MDM concept and also your strength of materials concepts, that is delta is equal to PL by AE, you must know. You cannot again derive how that PL by AE came. Okay, so is the case 6A delta by L square also you must know how that came. That Macaulay's method of double integration I gave you for boundary conditions I have applied and gave you. That you cannot do. You have to do now in the exam, tick it in 10-15 seconds, that's all. So now K33, we call it as flexural stiffness. It is 4EI by L. Then force at 2, because of this one you got, because of unit displacement at 3, 6EI by L square. Observe carefully earlier one. If you see the earlier point, what I have given you was this one. When I fix it, give unit displacement here, I call you this one as force at 3 because of displacement at 2, delta 2 it is 1 because of unit displacement. This you got it as 6EI by L square. See, K23 is 6EI by L square, K32 is also 6EI by L square. K23, K32, they are equal. This is from Bette's reciprocal work theorem. This is P system of forces, this is Q system of forces. Then from that, work done by P system of forces in Q displacements when you are taking. So, work done by P system of forces during the process of Q displacements must be equal to work done by Q forces in the process of displacing P forces system. They will be equal always and valid for linear elastic structures only. And we are taking stiffness matrix method is for linear elastic structures only. Non-linear elastic structures, we don't call it as stiffness method, simply displacement method. Once you are calling it as stiffness method, it means that you are applying it to linear elastic structures only. Okay. So, stiffness method, flexibility matrix methods are applicable to linear elastic structures for which the principle of superposition holds and deformations also must be small. Okay. So, we will see prove this one K23 is equal to K32 Maxwell's reciprocal, sorry, either the Betti's reciprocal work theorem. Okay. So, this observation we will keep it, then we have see that. Now, that point I will write here, this I remove. This is K32, why they are equal? This is also equal to K32. This is note we will write. This is what we have studied in strength of materials. What sir have told you is this one. From Betti's reciprocal work theorem. Again we will write applicable to linear elastic structures only. So, stiffness matrix method is also applicable to linear elastic structures only. This I gave you earlier 14th topic. I gave you about the energy methods I have given. Castigliano's theorem 1, if it is strain energy, Castigliano's theorem 1, if you take it, those two will give you displacement method and applicable to linear, non-linear elastic structures. If at all you apply theorem 1 and strain energy to linear elastic structures, what you get is stiffness method of analysis or stiffness matrix method. So many things from this. So, what is this Maxwell's reciprocal, Betti's reciprocal work theorem? Two systems of forces we will take. First system of forces is this one. A, B you have taken. You have given unit displacement here. This is displacement delta 2 became 1. Then this we called it as this force, this we call it, this is the coordinate 2 we have given. This is K force at 3 because of the displacement at 2, K32. This is actually 6 EI by L square. This what you got it, K32. This is a P system of forces, some P system. Next system is Q system of forces. Fix it. This is again coordinate 2. This is coordinate 2. This is coordinate 3. You have given unit displacement. theta became 1, or delta 3 is equal to some 1 I have given. Then because of that force developed here, you have calculated force at 2 because of the unit displacement K23 is 6 EI by L square, you got it. And here force was, this is K33 we have taken, you calculated this as 4 EI by L. And here K22 also you got it, how much? 12 EI by L cube. Now what reciprocal work theorem tells you is, work done by P system of forces during the displacement of Q forces must be equal to work done by Q system of forces during the displacements of P forces, like that. So from Betty, work done by P system of forces means how many forces we will consider? Say 2, K22, K32. Let us see. Here K22 is there. What's the corresponding displacement here? 0. So K22 into 0, because 0 displacement is there. Here K32 plus K32 into delta 3. Now delta 3 general term, we will make it as 1. This is work done by P system must be equal to work done by Q system in during the displacements of P system of forces. Now this one K23 here is there. How much it displaced? 1 must be equal to K23 here, K23 into corresponding displacement here delta 2. Force is Q system, displacement is P system, plus K33 into corresponding displacement, how much rotation here? Delta 3 in the first system is 0, because it didn't rotate at all. This is work done by Q system. So K23 into this delta, K33 into this rotation. Here is a fixed support, rotation is 0. Rotation is 0. So what you can write? Delta 3 is, you have taken delta 3 is unit rotation, delta 2 is unit displacement. Now you see, you will get K32 is equal to K23. That means from the Betty's reciprocal work theorem, always K23, K32 or K13, K31, they have to be equal from the nature of the reciprocal work theorem concept. That's why the stiffness matrices you are getting, they are always symmetric. Symmetric because of this Betty's reciprocal work theorem. Okay. So, sir might have told you many examples on that. I just forced you to recollect what is what is the Betty's reciprocal work theorem, whose a particular case of that is Maxwell's reciprocal displacement theorem. Maxwell's reciprocal displacement theorem deals with only single force. One force here, displacement in the other system. Multiple forces are there, then it is the Betty's work theorem. Okay. Now, you understood this one, why they have to be symmetrical. Next, fourth one is torsional stiffness. This I remove. Okay. Now, fourth one is torsional stiffness. We call it as K44. Force required or developed at 4 due to unit displacement at 4. This we know, this is the meaning of that, reading it. Or we can say force here means torque. Torque required to produce unit displacement means twist. Torque required to produce unit twist. This we know. Torque by theta. Theta means TL by Cj. That means twist, angle of twist formula TL by Cj we must remember, because after strength of materials only this will come. Cj is called torsional rigidity. Cj means torsional rigidity means what? Torque required to produce unit twist in a unit length of a member. Cj by L means is the torsional rigidity per unit length. You call it as torsional stiffness. Okay, that we give the number here K44. Otherwise, we don't deal with K44. Generally, torsional stiffnesses in the matrix methods we don't write it. But for the sake of completeness, this also I gave. So instead of simply writing it as torsional stiffness, give the number where you are applying force and where you are applying unit displacement and where you are finding the force. Like that. These are the types of stiffnesses. Okay. Next. Now, third point we will see third concept. Characteristics of stiffness matrix. Characteristics means if you build, first I told you how to develop all the stiffness coefficients. If those coefficients are written in a matrix form, we call it as stiffness matrix. First column of the stiffness matrix means at the coordinate 1, you give unit displacement. Because of that displacement, what are all the forces developed at all coordinates, you list them. To list them, you don't have to use Castigliano's theorem 1. Double time differentiation of strain energy not required. Strength of materials formulas are sufficient. Next, second column if you want, fix all the coordinates, only second coordinate give unit displacement. Because of that, what are all the forces developed, as I have explained, that will become second column. Like that, if you build, you will get a square stiffness matrix. To develop all the possible displacements, you have to restrain first, then give the displacements. That is the characteristic, that is how the stiffnesses are defined. You will get a square stiffness matrix, okay, and also symmetric. Symmetric means from the diagonal side, if you see above the diagonal, below the diagonal elements, they will be exact because of the Bette's reciprocal work theorem. Okay, those characteristics will write. First column, second column, how to build is, first column means first coordinate, you give unit displacement, fix all of them, find the forces. Those forces, if you list them, that is the first column. Okay, so to get first column of stiffness matrix, fix all coordinates, fix all coordinates and apply unit displacement. And apply unit displacement at coordinate 1. And find forces developed at all coordinates. Similarly, to get second column, apply unit displacement at 2 and find forces developed at all coordinates. Like that you build second column, third column also we can take it. This is the first characteristic. Second point is, if you build a matrix like this, you get a square symmetric matrix. Stiffness matrix is a square symmetric matrix. Square symmetric matrix. Then why symmetric? Symmetric because of Bett's reciprocal work theorem. What this means is symmetric matrix, it comes like this. Supposing that if you write say K, first column means like this. You give unit displacement at coordinate 1, find forces at all coordinates. Then how to read it? Force at coordinate 1, because of the displacement at coordinate 1. Forces at all coordinates means force at coordinate 1, force at coordinate 2, force at coordinate 3. K1, K2, K3 are the forces developed at all coordinates. Because of what? Unit displacement at coordinate 1. Unit displacement at coordinate 1. Second subscript is where you have given unit displacement. K1, K2, K3 are all the forces at those coordinates. From strength of materials only we will get the formulas. No Castigliano's theorem, no strain energy. Second column, forces at all coordinates are like this. K1, K2, K3. These are all the forces developed at all coordinates, but because of what? Unit displacement at coordinate 2. Second subscript tells you where the displacement is applied. Next, third column. These are all the forces developed at all coordinates, but because of what? Unit displacement at third coordinate. Like this. So, you will get how to read K12. Force developed at 1 due to unit displacement at 2. In which structure? Restrained structure, means symbolic representation of fixing the displacement structure. Then K21, force developed at 2 due to unit displacement at 1. Now, as I have explained to you earlier, from Betti, K12 must be K21. That is the meaning of symmetry. Now, third point is, if we take the diagonal, symmetry means that right? So all diagonal elements you take it, diagonal element with respect to the diagonal elements, if this matrix, if you fold it, these elements will exactly sit on that one. This and this equal, this and this equal, this and this are equal. That's why it is called symmetric. Okay. Now these diagonal elements are always a non-zero quantity and also positive quantity. Why like that? K11 force at coordinate 1 due to unit displacement at 1. In a structure, if you give unit displacement at coordinate 1, say, how force direction will be? If you are holding and lifting the beam up, let us say, then you have to lift it up. When you lift it up, it will not go down, right? That's why always, wherever you are up giving the unit displacement, at that point, force will be developed in the direction of the displacement only. That's what is Castigliano's theorem 1. Force at any, the first partial derivative of strain energy with respect to displacement at any point gives you force at that point in the direction of the displacement only. That means these are all, if a load and displacement are in the same direction, then that quantity is positive. But in case if you push it up at some other point, if it goes down, then that coordinate, that displacement, you take it as negative. If at all force and displacements are in the same direction, you will take that quantity as positive. If they act opposite to each other, we take them as negative. That's why these diagonal elements are always non-zero positive quantities only. It cannot be zero. If at all a stable structure is there, when you are lifting it up by 1, you have to apply some force. Without applying any force, with zero force, it's going, let us say, up by 1. That means it is a rigid body translation or rigid body rotation. So it is unstable structure. So for unstable structures, we don't define any stiffness matrix at all. Structures must be stable, then only stiffness coefficients you can find. Okay, that's why it is a non-zero. You have to apply, you require some force, and it is a positive quantity. So that is your third characteristic of a stiffness matrix. Stiffness, in the stiffness matrix, diagonal elements are always positive and non-zero. Non-zero, it cannot be zero. Zero means rigid body translation. Why like that? This is what you have learned from Castigliano. This again Castigliano's theorem. Just I am giving you the reason why they have to be positive and non-zero. From Castigliano's theorem 1, W is equal to dou U by dou delta. This is what I have given in the earlier chapters. That is first partial derivative of, why partial derivative? Because this energy you are writing in terms of not a single displacement. In a big structure there can be 10 displacements. Then with respect to first displacement, if you differentiate, that is called partial. Because this is not the only displacement happening in a structure. So first partial derivative of total strain energy with respect to displacement, at any point in the structure gives load at that point in the direction of displacement only. Okay, in the direction of displacement only. That's why they have to be positive and non-zero because it is a stable structure. When you hold it and lift it without any force, it goes up means it is a rigid body translation. That I think stability I told you without any without any resistance. If a body undergoes translation, it is called rigid body translation. If any structure undergoes rigid body translation or rigid body rotation, it means that this structure is unstable or mechanism. Okay, so then the applicability of theorem 1 I have given you applicable to linear, non-linear elastic structures. If it is applied to linear elastic structures, it is called stiffness method because you are getting stiffness coefficients. Why Castigliano's theorem 1 is called stiffness matrix method is by differentiating twice you are getting the stiffness coefficients. That means this what I think earlier I gave you double differentiation energy with respect to displacement. You got it as the AE by L. That means stiffness coefficients you get it. That's why Castigliano's theorem 1 gives you stiffness coefficients. So it belongs to stiffness matrix method of analysis. Okay, that I have already given you. Fourth point is this one. This I remove. Now, fourth point is this one. Assume that we have a member AB and you consider this member AB as axially rigid. Axially rigid means what? AE is equal to infinity. If you take a cantilever beam or any member as axially rigid means axially AE value are taking it as infinity. If it is axially rigid, can elongation happen? Whatever may be the force. Zero force, that means zero displacement. At a joint, if displacement is impossible, but if you give coordinate any number, let us say like this, you give coordinate 1, then what will happen? K11, P1 by delta 1. So P1 by what is the delta 1? 0. Something divided by 0 is equal to infinity. With infinity, what you will do? Nothing. That means at any coordinate, if displacement is impossible, then stiffness matrix will not exist. This type of quantities will come useless quantities. Okay, that's why I told you in the beginning, you must give coordinate numbers to all possible displacements only. If displacement is impossible, then give coordinate, then stiffness matrix will not exist. Okay, so conclusion. Coordinate numbers are given to all possible displacements. Numbers are given to all possible displacements only. If displacement at any coordinate is impossible, then stiffness matrix with respect to that coordinate system with respect to that coordinate system will not exist because of this problem. Okay, it will not. If with infinity, since you cannot do anything, so it is useless matrix you will get. Now, with this understanding of characteristics of stiffness matrix, in the examination, our task is in 2 minutes time to build or to write one stiffness coefficient, or at the most a 2 by 2 matrix you have to develop in 2 minutes time. Okay. Now let us see how numericals come on development of stiffness matrix. Now let us see the numericals. First one is stiffness coefficient K11 for the beam shown in figure. Now this is the problem. There was a hinge here, coordinate 1. This point let us say A, B, some C. This distance is A, this distance say B. Here 1, that is not a unit load, coordinate 1. It is coordinate 1, not unit load. So, on this beam, with respect to this coordinate system only, you must give the stiffness coefficient K11. Now, K11 means like this. What is K11? Force required at 1 to produce unit displacement at 1 when after fixing all other coordinates. In this case, he didn't give coordinate number 2, 3 for the slopes. Actually, for this problem, it can deflect, AC member can rotate, independent of that BC also can rotate. 2 rotations are there, 1 deflection is there. But for rotations, he didn't give any coordinate numbers, 2, 3 like that. So, we should not fix those displacements. You have to fix only the coordinates that they have given. With respect to that coordinates only, you have to find the stiffness coefficients. If the coordinates are given 2, 3 also say, then with respect to 3 coordinates, the stiffness matrix, stiffness coefficients, everything will be different. Okay. So, in this case, in this problem, there is only one coordinate. There is only one coordinate. So, don't fix any other displacement. That is slopes at CA and CB at C. Slopes we should not fix them. Now with this understanding, how we should solve the problem. Now see, combined problem, what we have to do is, for this problem, hold 1, permit the slopes to happen. Hold it, pull it down by 1. For that displacement, how much force we have to apply? That is called K11. But for a fixed beam with a central hinge, we don't know how to find that force. So split into two parts so that each part is known to us. This I take a cantilever, I take a cantilever say, then I pull it down. I know how to manage a cantilever instead of a fixed beam with central hinge. So I split this into two parts. A, this is C, this is coordinate 1, this length is A. Okay. Now, for this alone, I know how to find the load. If I apply a load W1, how it will deflect? Like this. This what I get is say delta 1. I know how to find that formula for delta 1. W1 into A cube by 3EI. But I don't want delta 1, I want delta 1 to be 1. 1 I want. Then what is W1? 3EI by A cube. If you apply 3EI by A cube amount of load, then delta 1 becomes 1. That's what from strength of materials. And you don't have to use Castigliano's theorem 1. Double differentiation not required. Now let us see the second part. This is C, B. Again this is coordinate 1. This length is B. Because when I am holding it and pulling it down by 1 unit displacement, both the beams deflect. That means you have to apply force required to deflect both the beams. That means both loads you have to add. So this load, now you take it as a W2. This is your problem. You go here and apply a load of W2. Then it will deflect. But I want this one now again delta 1 only. And this I wanted it to be 1. So delta 1 is equal to, for this beam, W2 into B cube by 3EI. Now this delta 1 I want it to be 1. So if I apply W2 is equal to 3EI by B cube, then delta 1 becomes 1. So since we have to add them K11, I have to deflect AC as well as CB, both I have to deflect. That means W1 plus W2 both I have to add, otherwise both beams will not come down. So K11 now stands for W1 plus W2. So the W1 is 3EI by A cube plus W2 means 3EI by B cube. So 3EI common factor if I take it, 1 by A cube plus 1 by B cube. So in 2 minutes time, your task is only this much. That you have to identify that K11 means force at coordinate 1 to produce unit displacement. If strength of materials problem directly you cannot apply, cut the beam into pieces so that individual members you will be able to manage. So for the delta deflection 3A, we know formula WL cube by 3A. Now I want delta to become 1. So directly we can find quickly. Okay. Supposing that if at all they have given coordinates 2 and 3, then I have to fix them, pull them down by 1 unit. Then the deflection profile changes, and those deflection profiles will tell you how much load you have to apply. Now in this case the deflection profile is like a cantilever because you permitted slopes to happen. So now deflection profile is like a cantilever. If not, accordingly we have to find the values. Now, supposing that if they give you this, I remove, how the values will change? Note K11. This is coordinate 1. This theta coordinate 2. This theta coordinate 3 they have given say. With respect to this 3 coordinate system, coordinate 1 is for deflection, 2 for theta CA, 3 for theta CB, because they deflect, they rotate. So when you are fixing them A, B, let us say this point is C, this point is B actually, no, C only, this is B. Now fix all the coordinates, push it down by 1. Now you have to fix it here, symbolic representation of fixing all the coordinates. Now give unit displacement like this. I wanted now delta 1 to be 1. Don't rotate now. Coordinate 2 should not be touched. This length is A. For this one we know force at coordinate 1. This is your first coordinate. This is second coordinate. Force at coordinate 1 to produce displacement also 1. For this profile to happen, we know it is 12 EI by A cube. Now second one is like this. If I fix here and here, this point is C, B, this length is B. Push it down by 1. Deflection profile is like this. This is delta 1. Again 1. For this one we know the force, also K11 only. 12 EI by B cube. 12. For this profile it is 12. For that profile it was 3. Now I have to add both. I have to pull this, I have to pull this. So both values I have to add. So your K11 is equal to 12 EI by A cube plus 12 EI by B cube. So 12 EI you take common factor, 1 by A cube plus 1 by B cube. Like this we have to write. Okay, now that means depending on the coordinate system, the stiffness coefficients also can change. Now let us see a continuous beam. For the continuous beam shown in figure, stiffness matrix with respect to coordinates. You see, with respect to the whatever coordinates they give us, with respect to coordinates shown in figure. Is. Now see, this is our problem. Actual structure is this one. Okay, this is 3 meters, this is 4 meters, I and I, A, B, C. These coordinates also they have to give us. This is coordinate 1, coordinate 2. In the beams and frames, generally axial forces, corresponding axial deformations are very less. So you can take them as axially rigid. If at all they give coordinate 3, coordinate 4 say, then axial deformations also you have to consider. If they are not given means the displacements are impossible, so no coordinate number is given axially. That means this beam is axially rigid but not flexurally rigid. Flexural things can happen but axially rigid. Such cases, what is dk? Dk is equal to 2, kinematic indeterminacy, theta A, theta B. So, these are the possible independent displacements. So, size or order of stiffness matrix K is nothing but dk by dk. That means if number of possible displacements are 10, say, that means dk is 10, then size of the stiffness matrix is 10 by 10. So, dk by dk, in this case you will get a 2 by 2 matrix. Sometimes this itself is a 2 marks question. What is the size of the stiffness matrix if members are axially rigid? If members are axially rigid. Now, next, so you get a stiffness matrix. First column we want first column of stiffness matrix. So, now we will take up stiffness matrix. First column. In the first problem, we will write how to get the first column. Next problems onwards, we will skip off that line. Because to become familiar, we are writing the procedure. To get first column, of stiffness matrix, what we have to do? Fix all coordinates. This is what I told you. Fix all coordinates and apply unit displacement at coordinate 1. And find forces developed at all coordinates. This is your first column. Now let us see how the first column looks like. Fix all coordinates means A and B are not fixed ones, but still we have to fix it. That is a symbolic representation of fixing all coordinates. That means this is this point, let us say A, B. Next, B, C. C is a fixed support. This is fixed support. But this is not fixed support. It is simply symbolic representation of fixing all coordinates. This we fixed it because there is a coordinate, so symbolically we have to fix it. At C already fixed support is there, you fix it as it is. So this and this symbolic representation of fixing the supports. Now apply unit displacement. This is coordinate 1. This is coordinate 2. If at B for the member BA coordinate 2, this coordinate 1 and 2 are given to the displacements. If theta BA is clockwise, say, theta BC has no choice, it has to be clockwise only. That's why, since coordinate numbers are given to given to the displacements, here also it should be same direction should be there. You should not give any coordinate number at C because it's a fixed support. If you give any coordinate number, displacement is impossible at C because it's actual fixed support. So if you give that C, even if you apply infinite moment, it will not rotate. But here, simply symbolic representation, just you with hands you are fixing it, rotating it, fixing, rotating, that's all. This already fixed support. No symbolic representation of fixing support, fixed itself. Here, temporarily we are fixing, that's all. So, apply unit displacement. If you apply unit displacement, how the deflected shape will go? Now, fix all coordinates and apply unit displacement at coordinate 1. This is symbolic 1, so it can rotate. This is like this. This is the, since it is symbolic representation only, I can fix without lifting up and down, hold it, rotate it by 1. This, since we know it is theta, or you can say delta 1. Delta 1 is 1. Now, how much force is required? You don't have to again use Castigliano's theorem 1 to find the force required to produce that theta. Because strength of materials, I told you, here also structures, I told you, deflection profile will tell you how much moment you have to apply. For this profile to happen, we know how much moment you have to apply. K, force at coordinate 1. To produce displacement also at coordinate 1, it is 4 EI by L. This much is applied. Then this will develop. When you apply this one, how much is carried over? Force at 2 because of 1, because of unit displacement at coordinate 1. This we know 2 EI by L. Why 2 EI by L came? From the carry over moment concept. And you applied here because it is fixed, it will take it, that's all. And this fixed support will not transfer anything to that. In air it cannot jump and that also it will be rotated, not possible. Okay, only that's all. This simply keeps quiet. This length is now here 4 meters. Now you see K11. I will read this one. From there to there, already when fixed support is there, say so stiff that any moment it comes, it takes, that's all. Will not transfer it to anybody. So K11. Force developed at 1 or required at 1. Developed at 1 due to unit displacement at 1. 4 EI by L. That means 4 EI by 3. Because of this unit displacement, force is developed here also. Force developed at 2 because of the unit displacement at 1. Force developed at 2 due to unit displacement at 1, 2 EI by L, from the carry over moment concept. That means carry over moment concept we should know, otherwise stiffness matrix methods of analysis of beams we cannot do. So this is your first column. Either they can ask you only what is K11 in 2 minutes time, or a 2 by 2 matrix quickly you have to build. Because I am assuming that you are learning it for the first time, so much story I have written. Next problems onwards, this story not required. What is K11, what is K21, directly you write the solution. Okay. Now let us see what is the reason for giving the same coordinate direction. Coordinate to here clockwise, there also clockwise. Why didn't we give anti-clockwise? That point is this one. Note. You see here, this is our problem. Fix it. This is the problem. When you apply load or any deflection profile you take, let us say, how the deflection profile will look like? Like this is deflected, let us assume. Okay, this is the tangent. This value is clockwise theta BC. This is also clockwise, you see, theta BA. A, B, C. You see here, if theta BC clockwise, theta BA has no choice. It has to be clockwise only. Okay, now coordinate 2 is given clockwise. Now here, when I give coordinate 2 clockwise, like this, you see this is clockwise 2 and this one is also rotating clockwise, so 2. Clockwise, clockwise. This coordinate number 2 is given to the displacements. So whatever direction it goes, this also goes in the same direction. That's why if it is clockwise, that should be clockwise. Since we don't know how much theta BA, theta BC, temporarily we'll fix it. Later on we will release it as in MDM. Okay. Now we are developing a stiffness matrix by fixing all the coordinate, all the displacements and find what is the force required to produce unit displacement. Then for theta displacement, how much is the force? Linear interpolation we will do and find in 2 minutes time. See here, since coordinate, this is the conclusion. Since coordinate numbers are given to displacements, coordinate 2 must be in the same direction. It must be in the same direction for span BA and BC, because theta BA and theta BC are in the same direction. Because theta BA, theta BC are in the same direction, coordinate 2 must be in the same direction. That same direction is clockwise or anti-clockwise. If you put anti-clockwise, say, here also anti-clockwise. If you put clockwise, here also it should be clockwise. That's why they have to give us which direction we have to take the coordinate number. So they'll give you whether to take clockwise or anti-clockwise. Then accordingly we have to fix it. We have to solve it. So this is about the first column. How to get stiffness matrix for the first column. Now let us see how to get the second column. Second column. To get second column, again you have to fix all coordinates. Fix all coordinates and apply unit displacement. Apply unit displacement at 2 and find forces developed at all coordinates. This is the process. Now you see, symbolic representation of fixing all the coordinates means is like this. Coordinate 1, symbolic representation. Coordinate 2, clockwise. Now this is actual fixed support. If this is clockwise, it has to be clockwise like this. This point, let us say A, B, B, C. 4 meters, 3 meters. So, symbolic representation of fixing the coordinates at A, B only. Fix, 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 actual fixed support. Now, apply unit displacement at coordinate 2. Wherever coordinate 2 appears, there you have to apply unit rotation, and what are all the forces developed you have to calculate. Now, if you apply unit displacement at 2, unit displacement means only rotation. So, like this it will go, right? For this, I want unit rotation. Here also when I push it, here also 2 is there, I have to rotate it. Then it will deflect like this. So, wherever coordinate 2 is there, you must give unit displacement. Now, for this profile to happen, here how much I have to apply? Force at 2. Unit displacement also at 2. This is 4 EI by L. Because of this carryover moment is force developed at 1 because of the unit displacement at 2. This is 2 EI by L. This is now COM. This is what we applied. For this we know, here also you have to apply to produce this one. Force at 2 because of the displacement also at 2. 4 EI by L applied. Because of this carryover moment will come 2 EI by L, that you don't have to write because there is no coordinate at all. Where there are no coordinates, there is no point in showing the forces because they will not come into our equations at all. So 4 EI by L. So K22, wherever 4 EI by L, K22 is there, you have to add them. So this is K12 directly I will write. K12 is 2 EI by L means 2 EI by 3. See K12, in this case K21, 2 EI by 3 same we got. K22, force at 2 because of unit displacement at 2. That K22s are at 2 locations in the beam, so 2 you have to add. 4 EI by L for BA span plus 4 EI by L for BC span. So this you will get 4 EI by 3 plus 4 EI by 4. So 7 EI by 3. This is 3, 4 plus 3, 7 EI by 3. This is K22. So now your stiffness matrix is like this. K. First column what we got is this one. K11 is 4 EI by 3, K21 is 2 EI by 3. Similarly, K, this is second column, force at 1 because of the unit displacement at 2. This is 2 EI by 3, this is 7 EI by 3. So 2 and 7 that we have written here. If I take EI by 3 common factor, 4, 2, 2, 7. This is the process. In this problem, we have written what is K12, K21, what it represents, how to find first column, how to find second column, why coordinate 2 is same direction, if he there clockwise, here also clockwise, so much story you have written. In the examination, this story we don't have to explain to anyone. This is for our understanding. We are assuming that we are learning for the first time. So I have told you how it should be written. Now let us see how to write for the frames. In the same way, we write for the frames also. Stiffness matrix for the frame shown in figure. With respect to given coordinate system. This point, let us say A, B, C. Loading they will not give you because the analysis will take minimum 5 minutes time to 6 minutes time. So that is not required. 2 minutes what you can manage we are giving. This is 6 meters I. 6 meters I. This is coordinate 1, coordinate 2. Okay. Now that entire story I told you we should not write. This what you have to show in the exam. First column. Fixing the coordinate system, all that story. Now we will not write. Quickly you fix this one. Call it as coordinate 1. And here also coordinate 1, coordinate 2. This point is A, B, B, C. This is 6 meters. This is also 6 meters. Now apply unit displacement. Unit displacement at coordinate 1. Then the deflected shape is like this. For this profile, this theta we want it to be 1. For this profile it is we know K11 4 EI by L. Here also I have to rotate. Then deflection profile will go like this. Beam or frame same way. Only thing is one member vertical, one member horizontal. Earlier problem both are horizontal. Other than that no difference at all. Now this is also K11. Force at 1. Displacement also at 1. 4EI by L. Then here carryover moment is there 2EI by L, but we don't write because there is no coordinate number. But whereas here coordinate 2 is there, so you have to write in the same direction it will develop. Force at 2 because of the displacement at 1. This is we know 2 EI by L from COM as a carryover moment concept. Now K11 4 EI by L for BA plus 4 EI by L for BC span, both spans. So this you will get 4 EI by 6. Next problem, this also you don't have to write, plus 4 EI by 6. That means you will get 4 EI by 3. Then K 2 because of 1. 2 EI by L is nothing but 2 EI by 6 is nothing but EI by 3. See, that's all is the first column. So we saved some time. Next, second column. Fix it. This is coordinate 1. This is also coordinate 1, coordinate 2, 6 meters. At coordinate 2, now you have to give unit displacement. Like this it will go. So for this profile, at 2 unit displacement means this is now theta, say 1. Force at 2, because of the displacement also at 2, we know it is 4 EI by L. This is like applied moment, and because of that how much is carried over? Force at 1 because of 2. This is 2 EI by L. This is in the form of carryover moment, K12 will develop. So K12, but from here to here in air it will not go and jump and try to rotate. So we have to leave it at that. So 2 EI by L, nothing but 2 EI by 6 EI by 3. Then K22, 4 EI by L means 4 EI by 6, that means 2 EI by 3. So your stiffness matrix will go like this. K11, 4 EI by 3. This is EI by 3, first column. Second column is EI by 3, 2 EI by 3. If at all you take EI by 3 common factor, 4, 1, 1, 2. Then how to save time is, suppose 4 options they will give you. In the 4 options, supposing that after finding first column, 4, 1, that means 4 EI by 3, EI by 3 you have calculated, 4 options were there. Only one option has 4, 1, let us say. All others are different. If second option is 4, 2, third option is 4, 3, fourth option is 1, 4, like that they gave, say. That means all the 3 options are wrong. Once this is correct, naturally this also has to be correct. So first column, if you do it, check the options. If only one option is there with 4, 1, you tick it. If 2 options are there with 4, 1, then it is like lottery. Then second column also you have to calculate and report it. So that is the process. You can save time. If at all only one option is available with 4, 1, first column only you do it and tick it. If 2 options have the same first column, then second column also you have to derive. That much work you have to make it. Now, after this is over, you will find that this, once you fix it here. For one problem you write it EI by 3, there also EI by 3. Only K22 you have to find. So, if you practice once how the problems are drawn, then second time when you are doing it, the speed with which you solve the same problem will increase. Since only either these problems or no problem, you solve it at least once or twice, then in the exam you can save a lot of time. You don't have to explain in the rough work to anything to anyone. Next we will see a simple 3 by 3 matrix, how it can be built within less time itself, because we are not writing how the K11 means, what is the meaning of K11, etc. The stories are gone. Now let us see stiffness matrix K. Assume that you have a simply supported beam. Okay, coordinates are given like this: A, B. This is coordinate 1, coordinate 2. Supposing that if the member is axially extensible, that means elongation is possible, I give coordinate also for that say. When I give coordinate 3 like this, it means that the member can elongate. If they give it as axially rigid and 3, then impossible to exist. In this case, 3 is given means there is elongation possible. So, first column, fix all the coordinates. This is symbolic representation of fixing all the coordinates 1, 2, 3. Now apply unit displacement at coordinate 1. How it will deflect? Like this. This is theta is equal to 1. For this one K11 we know 4EI by L, length span. Then carry over moment we know force at 2 because of 1, 2EI by L. When you rotate, actually this will not elongate, force at 3 because of rotation, 0, K31 0. Then second column, you don't have to list it directly, I am writing this one. This is called relatively doing the problem with fast. 1, 2, 3. Now second column means at second coordinate you have to give unit displacement like this. Now K22, we know it is 4EI by L. Because of this carryover moment we know K1 because of 2, 2EI by L. When I rotate, elongation is 0. Force at 3 because of this displacement is 0, K31 0. Next third column, fix symbolic representation, coordinate 1, coordinate 2, coordinate 3. So without rotating these two members, you fix here only and hold it, pull it by 1 like this, because it is symbolic representation of fixing the coordinates. This is delta 3, I can take it as 1. Because of this force at 3, because of unit displacement at 3, K33 we know AE by L, PL by AE. That means AE by L is the axial stiffness. Then when I am pulling it, how much moment will develop here? Force at 2, because of this elongation is 3. This one force at 1, because of the pull is also 3, 0, because no moments will develop when you are elongating. So these 3 are 0. So your K becomes like this. First column K11, 4 EI by L, then K21, this is 2 EI by L 0 over. Second column K12, 2 EI by L, 22, 4 EI by L 0. Here K13 0, 230, 33 AE by L. See, a 3 by 3 matrix also within our stipulated time we can manage, but till now they didn't ask you whether civil services or forest service or our engineering services. 3 by 3 matrix they didn't ask us. If they ask for such a simple case, they can ask you first column if it matches, then tick it directly without seeing the second and third columns. If two columns again same are there, two first columns are same, then you have to go for the second column also. Then once this matches, third you automatically we can get it. Now we will take a frame, one more frame we will take it. It is not necessary that always rotations only are the independent displacements. Translations also can be there. If the frames sway, then how we should write? The beams in the two-story frame shown in figure have cross sections such that flexural rigidity EI may be considered as infinity. What is the stiffness matrix? What is the stiffness matrix with respect to coordinates? With respect to coordinates 1 and 2. The frame is like this. This is coordinate 1, coordinate 2. Length L, L, like that they have given. This is the frame. Now you see, he has given that flexural rigidity may be considered as infinity. If flexural rigidity is considered as infinity, it does not mean that axial rigidity is also infinity. Flexural means only that you have to take it as infinity. For a beam, flexural rigidity infinity means it will not bend. As a rigid body, it can take moment, but it will not bend. It will only translate if possible. That's all. So he says that for this one, EI is infinity. This is also EI is infinity. Since EI is infinity, all rotations are 0. It can translate. If it translates by 10 mm, it will go by 10 mm only, because this member we will say that nothing is mentioned, so axial rigidity we will take it as infinity here in this case. Here also it can sway. Even if the members are flexurally rigid or axially rigid, as a rigid body they can sway. Sway can happen. So here and here only it can sway. So, and that sway is linear displacement. Accordingly, linear coordinates they have given. If rotation is independent displacement, say they will give you curved coordinate. So you have to get a 2 by 2 matrix with respect to this coordinate system. Okay. So if you want to get, say, first column, we will write for this one to have a better clarity. To get first column, process is same. Fix all coordinates, and apply unit displacement. At 1, and find forces developed at all coordinates. this is the process. Now you see how it will deflect. I will show it here for the better clarity. The meaning of this one. So right, this is our column. This is coordinate 1. This is coordinate 2. Symbolically fix the coordinate. All the coordinates you will fix it. This is called symbolic representation of fixing the coordinates. If I fix it, this cannot move. This also cannot move. Now, after fixing this and this, hold it, apply unit displacement. But rotations, there are no coordinates given. But still they cannot rotate because of EI value infinity. Because EI infinity, they don't rotate, otherwise they will rotate. And that rotated deflection curve means you will get a very complicated matrix. So, for this one, the deflection profile is like this only. Because EI is infinity. EI is infinity given. If it has to, you have to push it here linearly. This delta 1 is 1. If I push it as a rigid body, it will go also like this up to here. When I am fixing here, this also fixed. Behaves like a fixed one. A is infinity. So the deflection profile is like this. If you draw the deflection profile correctly for this unit displacement, your stiffness matrix will never go wrong. Because for that deflection profile, you know how to calculate all the known deflection profiles only they are. An unknown deflection profile in the exam they will not ask. Okay. So this is 1 means this is also 1. It will also undergo same 1 displacement. For this one, we know how much moment will develop here. 6 EI by L square. Here also 6 EI by L square. Here also, you see, though it is no coordinate is there, but moment will develop 6 EI by L square. Here also it will develop 6 EI by L square. And force developed, again I told you how much force is required. Actually it is 12 EI delta by L cube, where delta is 1 now. This is now 12 EI by L cube. This plus this by L. Here also same. 12 EI by L cube. These two are anti-clockwise. So clockwise couple will form. Clockwise means this is right side, here it is left side. This is 12 EI by L cube. Here also left side force will develop. With this free body diagram is complete. Now you see K11 means at the coordinate 1, what is the force developed? Because of the unit displacement. You see here when I am pushing it here, this also will get pushed. Without this being pushed, this alone cannot move right side. That means you have to add this force also, otherwise this fellow will not move. If this fellow doesn't move, this fellow also can't move. So when I am pushing it, all of them will move. So what is the force required is also you have to calculate, and that becomes K11. At one level, what are the forces developed? You have to add. So K11, 12 EI by L cube plus 12 EI by L cube. You will get 24 EI by L cube. Now K2, force developed at 2 here because of that one displacement K21. Now you see coordinate 2 is right side, but the displacement is left side. That means coordinate 2 is right side, but force is left side. So you have to take it as negative. Minus 12 EI by L cube. This also minus. Why we are adding is this automatically develops at coordinate 2 location. We will write the reason. Negative because coordinate 2 and force are opposite to each other. So you will get minus 24 EI by L cube. This is plus 24 EI by L cube. This is the first column. Now let us see the second column. To get second column, fix all coordinates and apply unit displacement at 2 and find forces developed at all coordinates. Now let us see what it means. Fix it. Okay. Fix this coordinate. Fix this coordinate. Coordinate 1, coordinate 2. Lengths are L and L. Now see, now you have to fix this one and also this already fixed support. Hold this, push it by 1. Then if I push it by 1, this also goes by 1. Otherwise, this alone cannot contract. So the deflection profile for this unit displacement is now like this. Okay. Now this goes by 1. Now it is fixed. It cannot sway now. Like this it will go. Same way here also. Once you fix it means this cannot move right side. But this can go right side by 1. It is now symbolic representation. Like this it will become. This also delta 2 is 1. Is 1. For this profile, moments we know here 6EI by L square. 6EI by L square. Now here also moments will develop because of this sway. This is 6EI by L square. And here to make the slope 0, here it will develop clockwise. How much? Same. 6EI by L square. Here also clockwise. 6EI by L square. Here also clockwise. 6EI by L square. Here also you are fixing it. So 6EI by L square. So individually 4 columns they develop like that. Now moment forces. We are not interested in the moments, but without finding moments we don't know the force. We forgot, let us say. Then both of them are clockwise. So here anti-clockwise couple will form like this. If this is clockwise, anti-clockwise couple, individual free body diagrams we can take it and the forces can be clubbed. Because principle of superposition you can apply. These deformations are not large. Okay. So this is now 12 EI by L cube. This also 12 EI by L cube. Here clockwise, clockwise. So anti-clockwise. If this is clockwise, anti-clockwise couple should form. 12 EI by L cube. Here right side. 12 EI by L cube. This for the top floor. This one you see anti-clockwise, anti-clockwise. To balance it clockwise like this. Independent of this, this will develop. 12 EI by L cube. Here also 12 EI by L cube. Here anti-clockwise, so clockwise. 12 EI by L cube. Here also 12 EI by L cube. Since coordinates are not here, we don't have to deal with them, but this you have to deal. Coordinate 1 right side, but forces are left side, so negative you have to take. Force at 1 because of the displacement at 2 is minus 12 EI by L cube minus 12 EI by L cube. So you will get minus 24 EI by L cube. K22, force at 2 because of the displacement at 2. This is 4 are there. So 12, 12, 12, 12. 4 12s are there. So 4 I am writing directly. 4 into 12 EI by L cube. So 48 EI by L cube. So your stiffness matrix becomes CK11. 24 EI by L cube. This is minus 24 EI by L cube. This is minus 24 EI by L cube. This is 48 EI by L cube. If you take common factor 24 EI by L cube as a common factor, 1 minus 1 minus 1, 2. In the exam, one of the option is this one. There, even here also, if the first column, 4 options are there, in the 4 options, only one option matches with the first column, say, then stop it. Second column you don't have to do. If 2 options have the same first column, then you have to do the second column also. Otherwise, it will look like a lottery. Shall we answer A or B? The same first columns are there. So that's how in the exam you have to see the options. Sometimes they will let you save your time. So this is about the beams and frames, how to form the stiffness matrix. Either translatory displacements are there or rotational displacements are there. For beams, frames and multi-storied frames also it will go like this. Any one they can ask, one coefficient or a 2 by 2 matrix. That is only scope in the matrix method. Complete problem you cannot solve it. Even in the mains also they will not ask you because of the lack of time. 2 by 2 matrix, if you have to develop and solve it, say minimum, it will take say 10 minutes time. Even 20 marks questions nowadays they are not asking for 20 marks questions. 10 minutes means too much of a time in the exam. Okay. Now we will see the how to analyze analysis of redundant trusses by using stiffness matrix method. If at all in the examination any redundant truss is given, means indeterminate truss is given, that has to be solved by the stiffness matrix method. Otherwise, within our stipulated time, you cannot analyze indeterminate trusses.